Good afternoon, class. Today is October the 25th, and so this is the lecture for October the 27th, and it's a review for the quiz, for quiz 2, which is on October 29th. And so what we're going to do is I'm going to go ahead and just get started on the review, because as we do homework 6, we'll be reviewing the diffusion section. So there's three parts to what we're going to cover. There's etching. All right, and so for wet etching, I mean, what I want you to know or have gained from the class material is that there is wet versus plasma. And so for wet etches, we described using acids for some 3,5s. And for plasma, that's for silicon, silicon oxide, silicon nitride, and for patterning, which etch mask to use, and that's photoresist. I'll write out photoresist. Versus silicon nitride. Where photoresist is used for many liquid etches, and also for silicon nitride. All right, SINX. Plasma. And silicon nitride is primarily for 3,5 plasma. Now we didn't really get much into okay, you can read that barely. Sorry for I'm going to try and put everything on the same board here. So basically, we didn't cover many recipes, so to speak, and rather I just wanted to give you a general understanding that etching can be done in a beaker with a liquid acid or base, or it can be done using a plasma and a reactive ion etcher. There's also ion beam, which we covered briefly. But for your work in the clean room, it's primarily either a reactive ion etcher RIE, or it's doing a wet etch in a beaker, and so there's these considerations, which is what type of etch to use. Now, plasma will give you better sidewalls, So more straight sidewalls from the etch, whereas a wet will tend to be, I'll try to put it over here, isotropic, or it will undercut. So that sort of tells you that if you want well-defined, straight sidewalls, you usually favor a plasma. But if you're willing to tolerate some undercut, and in fact, sometimes you want undercut, you want that. You can use a liquid etch, which is sometimes simpler, and there's sort of A sub or A prime. We also talked about KOH etching of silicon, which is a crystal plane. Stops on 111. So there's sort of kind of three things. There's what type of etch to use, wet versus plasma or an ion beam. There's what mask to use, which is well, whether to use a photoresist, which works for many liquid etches, or silicon nitride plasma etch, or using silicon nitride for an etch mask, which is usually needed for plasma etching of 3,5 semiconductor. And that's the sort of the main things about etching that we got to. Now then, second thing is wafer cleaning. And for wafer cleaning, we primarily, we talked about what you're trying to clean and how most of the time you don't want to clean, but because cleaning can actually make things dirty. But we talked about mainly two things for photoresist. Sorry. Acetone, methanol, isopropyl. Wow. Okay, and that's because acetone dissolves the photoresist, but acetone will leave a residue. So you then put it in methanol, which dissolves the acetone away, but methanol will leave a residue, so then you dissolve it and put it in isopropyl, which will dissolve the methanol. And we also talked about the RCA for silicon, which is ammonia, this three-step of ammonia, H2O2, which removes your organics, an HCl, and then an HF base. So, and we talked about various other things with regard to wafer cleaning, just for your own information in the clean room. Rinsing is sort of a variation of wafer cleaning. We talked about that a little bit. All right. Now, the two main things that we covered, actually, since the last quiz, are first, oxidation. And for that, we talked about learning that there's this profile of the concentration of oxygen versus depth Z. And you were taught that that profile is linear, and that there's a depth capital Z, and at that depth you have a concentration C sub Z. And the main thing you learned is pretty straightforward to sum up. you learned that at Z equals Z, the reaction rate is equal to two things. It's equal to the rate constant times the concentration at Z, and it's also equal to the flux, which is minus D dc dz. So if you remember those things, okay, then you can pretty much figure out everything you need to do. Now we used that, and we went through using the molar mass to derive that Z versus time, negative Z naught plus Z naught times the square root of 1 plus T over T, where Z naught is defined as D over K, and where do I have it here? Yeah. And that T is defined as D over 2 the molar volume K squared CS. So those are the main two things to know, and if you know those things, you should be fine in the quiz. I mean, basically, I will ask you some question relating to those aspects, and you'll have to know them. And in particular, note that if this is the profile at one time, okay, we went to great pains to make sure you understood that, okay, as you go deeper, so at a later time, right, Z has increased, that the slope has decreased, the absolute value of the slope, okay, and also C sub Z has decreased. And that's directly follows from the fact that, okay, since the slope has decreased, C sub Z has to decrease. And so you can use that to evaluate a correct profile of oxygen versus time and distance. Okay, so, that's really all we need to know about that. And then for diffusion, and so for diffusion, just looking here. Okay. Let's just go through the homework. So let's do homework 6. So problem 1. For problem 1, this is a. I'm gonna start using the term gas on, meaning that the dopant gas is on diffusion, for which you learn that N of X is equal to N at the surface, which is determined by the gas, so that's fixed, times 1 minus ERF of X over L, where L is the square root, 2 times the square root of D times T. So L is the diffusion length which goes up at the square root of time. And problem 1, let me write that out better. Actually, let me put that up here. Where D is the diffusion coefficient. And so problem 1, you were asked to use the piecewise linear approximation for ERF to evaluate Q, the dose. And the ERF function, I'll write ERF of X prime, versus x prime goes up as 2 over root pi x from the origin, and then it has to turn over because it can't go bigger than 1. And so basically, if you write out n of x, it starts at ns, and it goes down linearly, and then it has to turn over like that, because it's 1 minus ERF versus x prime, where x prime is xx over L. And so you can draw a straight line through that then, like here, and so that's basically going to reach 1, right? This is going to reach 1 at square root of pi over 2. And so Q is the integral of n of x dx. And so based upon this approximation here, it's the area of that triangle. So it's ns times, okay, so that's where x over L, and so if you plot it versus, let me replot it versus x, just so we're perfectly clear. So basically, for it as a function of x, right, then this is where x over L is equal to root pi over 2, or x is equal to L root 2 pi over 2. So the actual n sub s does this. Oops. Okay, and the approximation was to do that, and so so Q is the integral of n of x dx over all space, sorry, and so that's equal to, in the approximation, ns times 1/2, because the area of the triangle, of L root pi over 2, and so that's equal to square root of pi over 2 L and S, or if you work out the square root of, oops, that's before, square root of pi over 4. So the square root of pi over 4 is, square root of pi is like 1.7. So that's a little under a half. So that's basically 0.443 L and S. So that's your answer there for that problem. And in the book, okay, actual Q from the integral of the error function, that, we didn't show you how to integrate the error function. That's why I'm kind of doing this problem. The actual Q works out to be, well, it's 1 over the square root of pi NSL. And the pi's here kind of are, don't get confused about the pi's here, because, here it was square root of pi over 4 LNS. The actual answer is 1 over root pi NSL. And so, don't get hung up on the pi's here. Just get the actual value there. 1 over the square root of pi is 0.564 LNS. So it makes sense, because the actual n versus, it has this tail out here. So the actual Q is somewhat bigger than this piecewise linear approximation. Just checking my focus. It's roughly okay. I don't want to fool with it right now. Okay, hopefully it'll find itself. Okay, so that was the answer basically. Now number 2, okay, you were actually calculate D. So D is D naught times e to the negative EA over KT, okay, from the notes. Okay, my focus came back. All right, so you were told to use the average, and in the textbook there's one value for D naught, and in the notes there's another value, and so you use the average. So that's 4.28. Okay, is the average of those two values. Times e to the minus. The average EA is 3.67 EV, and KT at 1000 centigrade works out to 0.11 EV. And so the answer for D is 1.39 times 10 to the minus 14 centimeters squared per second. Now, you were then asked to calculate L, and L is the 2 times the square root of dt. So at 1 hour, of course, I mean, you have to plug in, so for seconds, for 3600 seconds. That works out to 0.141 microns. And so Q from here is equal to, you multiply 10 to the 19, well, I mean, I won't write the numbers, 7.95 times 10 to the 13, 1 over centimeter squared. So this is the number of dopant atoms per area, per surface area. That's what Q is. All right, now and then you were asked to plot. Okay, so what I'm going to do is, see, I'm trying to put everything on one set of boards here, and so you were asked to plot N. And I asked you to do it in a semi-log plot. So N, if you start with 10 to the 13, 10 to the 14, 10 to the 15. Oops, I'm going too low. 14, 10 to the 15, 10 to the 16, 17, 18, 19. Now I can fit it all in. 10 to the 19th. So N goes as a surface times 1 minus ERF of x over L, and L is where was it? Yeah, 0.141. So I'm going to make my plot 0.5, 1, 1.5, 2, 2.5 microns. Now, as I had said it, giving you sort of a hint in the handout. Okay, in calculating N, that's the second problem. Okay, so, and if you did the plot of 1 minus ERF of x over L for L equals 0.141 microns, you would have got something like this. Okay? And you'll see there's a reason why I extended it out here, because of the third problem. And for this problem, Q is equal to 7.95. 13. So problems, problem one was just to get you more familiar with the error function really more than anything else. But problem two shows this is a gas on diffusion. Now for problem three, you turn the gas off and you perform the diffusion at the same temperature. You start the timer over and I wanted you to go for 9 hours and also for 25 hours. Okay, and I wanted you to plot that on the same scale. So let's see if we can do that here. 10 to the 13, 10 to the 14, 15, 16, 17, okay. So now N in the second step is 2 over root pi Q over L e to the negative x squared over L squared. Now, you have to remember there's a new L here, and I don't want to start putting subscripts and stuff because the timer starts over again. And I hope that was clear. That's what I tried to make the point in the last chat session, that in the second step you start the timer over again. So there's basically, at 9 hours, L is, because L goes to the square root of time, because the diffusion coefficient is the same, because we're at 1000 centigrade. So at 9 hours, L is 0.423 microns, and for 25, L is 0.705 microns. Now, in this formula, and that was the hint, kind of, okay, because Q is in inverse centimeter squared, here you want to put L in centimeters, not microns. And so, whereas here, because you're plotting versus X in microns usually, you want L in microns. Okay, and if you do that, what I got, okay, 10 to the 18th, okay, is, just write my markers. So 0.51 to 2.5. So that's 3 hours. And then for and I kind of messed up my plot just hand drawing it, but this is 3 hours. And this is 9 hours. Oops, other way around. 9 hours, taking the square root of my head, and 25 hours. So you can. I'll be posting the solution as soon as I upload the video. But basically, what happens is that you started at 10 to the 19 on the surface, and at 9 hours that goes down to some value a little above 10 to the 18. At 25 hours, that goes down to 10 to the 18. And you basically take that and you spread it out. So the surface has to go down, and it has to spread further into the semiconductor. And the important thing to remember is Q doesn't change. Right? You put a certain dose in there, Q, which is the integral under that curve, and all you're doing is you're spreading it out, and you're spreading it out so that if you want like a junction depth at 2 microns, you can plug in and determine how long you have to diffuse in the second step to get the dopant up to whatever you want it to at that distance. And that's all I was going to do as far as a review for diffusion, because it's basically knowing those things. All right, so the quiz will be like the first quiz. It'll be about 8 questions, and I've made up the quiz. It might involve a few more calculations than the first quiz because of oxidation and diffusion. But all the information is here on the board. The quiz is totally open book, in the same format. You'll be, emailed a file at the start of class on Thursday, and then you return it to Chris and myself, and that's it. Okay, so that's the extent of the review, and everything is here on the board that you that you need to know. All right.